to say that it's hard to go back to work after yesterday's beautiful excursion. Especially it's hard to move my legs. So today I will try to... I'm sorry, I have to change some... So today I will try to translate in practice what I discussed the other time on a general level. So this means I will try to discuss I will try to discuss the MSSM, which is the minimal extension, supersymmetric extension of the standard model. But before doing that, I have to add a last ingredient. And before adding the last ingredient, let me summarize what we saw the other time. So, in brief, we said that the supersymmetry is a symmetry which relates fermions and bosons. We said that in a quantum field theory, our fields must be grouped in what are called superfields, that are multiplets of fields, in this case doublets of fields. And we have essentially two doublets. So the fields that appear in our Lagrangian are either part of what is called a chiral multiplet of fields that contains a scalar and a spinor, or they are part of a so-called vector multiplet, vector superfield, which contains a vector and a fermion. And then I discussed very shortly how to write the most generic gauge Lagrangian, gauge supersymmetric Lagrangian, and this is the formula. What's important here is not the details of the formula, but just the fact, if you want, that this expression, the Lagrangian, is determined by the gauge structure of the theory and a function, this W, which is called the superpotential. Now the new ingredient, which is supersymmetry breaking. I mentioned already the other time that the supersymmetry has to be broken, because we saw that in supersymmetry every boson is accompanied by a fermion, so in particular, and vice versa. So in particular, the standard model particles should be accompanied by partners that have a different spin and have the same mass. And certainly we haven't observed anything like that. For example, the electron of the standard model should be accompanied by a supersymmetric partner, which you call the selectron, and the mass of this supersymmetric particle, which is denoted by ME with the tilde usually denotes properties of the supersymmetric particles. So the mass of these supersymmetric particles, if supersymmetry was exact, should be the same as the mass of the electron, which is not the case. We know experimentally that the mass of the selectron is larger than about 100 GeV, which means that the supersymmetry must be broken. How do we break supersymmetry? We don't know. We don't know very well. This is the part of the theory which is less understood, in the sense that we have many mechanisms available, but we don't know exactly which one is the one that we should use. What do we know? We know, first of all, for sure that we would like to break supersymmetry spontaneously. We like much better breaking symmetries in a spontaneous way than in an explicit way. You remember the difference. A symmetry broken in a spontaneous way is a symmetry of the Lagrangian that is broken because the ground state is not invariant. An explicit breaking of the symmetry is when you really add a piece in the Lagrangian which is not invariant. So the Lagrangian itself is not invariant. So we would like to preserve the invariance of the Lagrangian and break it spontaneously. And that is possible. That is possible, and so we believe that that's what happens. However, there are different constraints on the precise way in which this can be implemented, and this means that, for example, that the breaking of supersymmetry should happen at a very high scale in a sector which is separated from the sector of the fields that we observe. So, simple words, we don't actually know what happens. However, fortunately, it's possible to parameterize, if you want, the effect of any type of supersymmetry breaking which happens at the high scale by adding to the supersymmetric Lagrangian that we have already seen, L SUSY, another piece made of terms that break explicitly supersymmetry. So these are pieces that are not invariant under supersymmetry in the Lagrangian. However, although they break explicitly supersymmetry, they are there, and their purpose is to parameterize the effect of the most general spontaneous breaking of supersymmetry, which happens at a higher scale. Since we don't know exactly what is this mechanism that breaks supersymmetry and communicates the breaking of supersymmetry to the fields that we observe, we just parameterize it by adding another piece to the Lagrangian, which is called L soft, which contains the so-called soft supersymmetry breaking terms. Why are these terms called soft supersymmetry breaking terms? Well, because you see, when you add terms to the Lagrangian that break explicitly supersymmetry, you may lose the properties of supersymmetry, of course. And one of the important properties of supersymmetry that we care about is the fact that in supersymmetry there are no quadratic divergences. So now, if we add these pieces that break supersymmetry, of course the first question is, are we reintroducing quadratic divergences? And instead, this is not the case. These terms are called soft because by definition they don't reintroduce quadratic divergences in the theory. So you're breaking supersymmetry, but you keep this nice property that you don't have quadratic divergences. In fact, this is the most general list of terms that you can add that break supersymmetry and don't introduce quadratic divergences. These terms are all characterized by the fact that they are proportional to a mass term, or to a mass squared, and these mass terms characterize the scale at which a supersymmetry is broken. So let me describe these terms in a little more detail. What you can have is a generic mass gauge invariant, of course, a mass term for the scalars. You remember, AI was the notation for the scalars of the theory. Then you can have a mass term for the gauginos. You remember the gauginos are the fermions that are partners of the gauge bosons of your theory. And you can have a generic mass term for that. That was forbidden by supersymmetry. And then you can also add a generic holomorphic function of the scalars of your theory. This resembles a little bit the superpotential that I had introduced in the last lecture. However, the superpotential doesn't appear directly in the SUSY Lagrangian. It's only a combination of derivatives of the superpotential that appears in the Lagrangian. Instead, this object here appears directly in the Lagrangian. So this,
what is the difference between M term and B squared term?
Between, sorry?
M squared term and B squared term. It's the same.
No, this is holomorphic, so it doesn't include the conjugate of the field. And this instead is in the form A dagger.
Okay.
There are actually other terms that you could add, but you can always reabsorb it, so this can be considered general enough. Yes. Okay, so this was the last ingredient. So we had described the supersymmetry part of the Lagrangian here, and then this is the soft Lagrangian that you can add. As you can see, things are a bit complicated. The Lagrangian that you obtain is pretty complicated. However, I can assure you that it's still way less complicated than the use of this Kartoshka game that I played.
What means Mikasa? What is it? Mikasa.
This is a
Oh,
ball.
no, it's just a
Ball. What is it?
okay, so now, as I promised, I switch to something a little bit more practical, the MSSM. So that was the description of the most general supersymmetry theory. But now, if supersymmetry